Okay, I think for the sake of repeating it, I will do it again. So, what we are trying to do today is to focus on the process hazard analysis part of it, which is a subset of the larger hazard identification process. Okay. So, the agenda will be a bit of introduction on why this is important and also how the Indian statutes are trying to address the aspect of process hazard analysis, and we will have a brief discussion about a case study, because this is something which you will be able to have a practical understanding. If you do not do a proper process hazard analysis, what will happen, how it is going to impact your day to day operations, and then of course, various techniques which are used in terms of both hazard identification and hazard analysis. And of course, we will have another case study largely to understand one of the important techniques, which is HAZOP, like if you do not do a proper HAZOP, how it is going to impact the operations. So, this is the agenda for today. Maybe perhaps tomorrow Mr. Karthikeyan will take you through 2-3 PHA techniques in a very detailed way of how it is applied in the day to day operations. Okay. Before we start this particular thing, I wanted to have your views on how far you have understood the difference between process safety and occupational safety. I think this is week 6, right? Okay. So, what is the difference in your own understanding between process safety and occupational safety? Both are same or both are different?
Both are different.
Very good.
Safety involves the safety measures basically in you carrying out a process, whereas occupational safety is how you protect yourself from any hazard that could possibly happen in an industry or in an environment where you are working.
Okay, fine. Anything more? What was the Bhopal incident? Was a process safety incident or an occupational safety incident? Why do you say so? What stands out in that incident? Correct. No, that is okay. What was the effect? What happened because of Bhopal incident? High severity. Correct. Okay. So, one other key difference between a process safety incident and an occupational safety is that in a process safety incident, the degree of severity that we are talking about is the magnitude is so high, like it could be multiple people getting affected, whereas in an occupational safety incident, it could be related to your frequency may be more, but the severity will be relatively of a lower magnitude. Okay, fine. So, now why that is very important is, like, unless you understand the difference between both, the hazard identification techniques which are applied are also equally different. So, that is the reason why I want you to get this fundamentals very clear. Otherwise, there will always be a clash in terms of when do I use this particular technique. So, tomorrow you go to the industry and you see that they say, like, I have used this technique to identify this hazard. You will not be able to correlate and say whether that is the right technique, whether it has been done in the right method or not. Now, like how for the whole human body, the heart is a very important aspect, or the brain is a very important aspect. When you talk about process safety, PHA or the process hazard analysis is the single most important element. The reason being that if you are not able to identify your hazards properly, if you are not able to identify them properly, you cannot control them, you cannot mitigate them. So, you will have a risk which you will be carrying at all point of time. So, a PHA is a single most important aspect of the overall process safety management system. Okay. So, it forms the basis around which variety of other elements, you talk about your training, your work permit system, your management of change, your process safety information, accident investigation, all of this revolves around your process hazard analysis. Now, having said that, another question which I wanted to ask you is that, is implementation of a process safety management system mandatory in India? I think you did have a session on statutes, right? I think my colleague Sindhil perhaps took that session. So, what is your understanding? Is implementation of a process safety management system mandatory in Indian industries? There are standards, but it is not mandatory. Okay. Any other views? You have referred any of the statutes, like I have listed some 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Any of these you had an opportunity to go through, at least glance through in terms of what are the broad contents? See, PSM is not mandatory in India. The whole of process safety management system, which is mandatory in the United States, is not mandatory in India as per law. The law does not require you to implement a process safety management system in totality, whereas there are a number of statutes which talks about the need for the industry to carry out process hazard analysis in an in-depth way, document it, act upon the recommendations which are coming out of those process hazard analysis, and prove to the statutory authorities that you are operating your plant in a systematic manner, and thereby you have systems in place to control those risks. Now, which are those statutes which are talking about it? All of these. Okay. For example, it starts even from your Fundamental Factories Act. Then you have the manufacture, storage and import of hazardous chemicals rules. Now, this is one of the most important statutes, the manufacture, storage and import of hazardous chemical rules. This came into being after the Bhopal incident. After the Bhopal incident happened, this is one of the laws which was framed. And today, as per this law, if any industry, for example, you take LPG, if you store more than 100 tons of LPG in bulk storage in your facility, you will fall under the ambit of this particular law. You are expected to do a process hazard analysis, and then you are expected to act upon the recommendations arising out of it. Similarly, these are the other things which talks about few of the other statutes which talks about the need for doing a process hazard analysis in the industries in which it is applicable. Okay. Now, this is a broad timeline. I think maybe in various forms you would have seen it earlier. See, this is how the whole industry has moved. You know, we've always learned from the accidents. There is no shame in admitting that it is not about India. If you look at it, last 5 years, yes, India has had its own share of major accidents, but then if you look at the number of accidents historically which has happened even in the developed economies, it is high. Okay. So, it is not about the maturity of a particular industry, it is more in terms of how the industry has been able to sustain the standards which has been practicing for a long period of time. You can look at in terms of, like, you know, from the mid 70s to 80s, you have the Flixborough, the Seveso. I think you would have heard about many of these incidents in the previous classes, right. You know that these are where the incidents which shaped what I would say the elements of process safety management over a period of time. You come back to 1996, it talks about ISA S84 US 1999 2003. Okay. Maybe yes, I think late 2010 also one of these standards got updated. So, over a period of time, depending upon the nature of incidents that we have had, the industry has adopted the learnings from it, has fine tuned its statutes to ensure that the learning has been captured in it to make it more rigorous, and that is how the industry has progressed. Now, before we get into this process hazard analysis, I wanted to discuss about a small case study here. I think it doesn't work. Yeah, just it. Before we start playing that, what I want you to carefully observe in this video, it actually reconstructs the event which happened in BP Texas refinery in the United States. Okay. It does an accident reconstruction for about 8 to 9 minutes. carefully observe what has happened in that. Okay, so I wanted to have a brief discussion, because if you are able to fully understand what is said in that video, then what we are going to discuss subsequently will be very easy for you to have an overview in terms of why it is important.
Isomerization or ISOM unit, which produces materials to boost the octane rating of gasoline. The explosion shattered windows in homes and businesses up to 3/4 of a mile away from the 1,200-acre refinery. As thick black smoke billowed from the plant, authorities instructed some 43,000 Texas City residents to stay indoors. The accident caused BP billions of dollars in victims' compensation, property damage, and lost production. This investigation was the largest and most comprehensive investigation in the history of the Chemical Safety Board. CSB Supervisory Investigator Don Holmstrom led a 2-year investigation to determine the root causes of the accident. We interviewed over 370 witnesses. We looked at thousands of documents, literally millions of pages of documents, and we examined the plant, inspected over 40 pieces of instrumentation and equipment. The investigation team examined a wide range of safety systems, practices, and standards, and looked at human factors such as fatigue and communication between operators. The board's report was released at a public meeting in Texas City on March 20th, 2007. Then CSB Chairman Carolyn Merritt presided.
Many of you here tonight had family members or co-workers who were victims of this explosion. To all of you, I express my deepest condolences and sincere wishes that society never allows another accident like this to occur.
The tragedy at BP was the worst industrial accident in the United States in nearly 15 years. The CSB concluded that it was the result of organizational and safety deficiencies at all levels of the company. We found that BP management had, for many years, overlooked warning signs of a possible catastrophic accident.
There's an old saying that if you think safety is expensive, try an accident. Accidents cost a lot of money, and they not only damage the plant and the claims for injury, but also the loss of the company's reputation.
The reason why the Texas City accident had such an impact is that states will feel that couldn't happen to me, and the ones that feel that that couldn't happen
I'm
to their
skipping
son
few of the things because I want to take you to the animation.
Some of the other refineries within the United States will feel that couldn't happen to me, and the ones that feel that that couldn't happen at their site is the ones that are set up to have it happen there.
The following CSB computer animation depicts the sequence of events over an 11-hour period leading to the explosion at the BP Texas City refinery on March 23rd, 2005. Several units at the Texas City refinery had been shut down for lengthy maintenance projects, which required nearly 1,000 contractors to be on site along with BP employees. BP had positioned a number of portable trailers close to process units for the use of contractors and other maintenance workers. Over a period of months, BP had located 10 trailers for workers servicing the ultra-cracker unit, including a double-wide wood frame trailer that contained 11 offices and was regularly used for meetings. Though these trailers were located near the isomerization unit, the occupants were not warned the ISOM unit was about to start up, a potentially hazardous operation. At 2:15 a.m. on March 23rd, overnight operators began introducing flammable liquid hydrocarbons known as raffinate into a 170-foot tall raffinate splitter tower used to distill and separate gasoline components. Near the base of the tower, there was a single instrument that measured how much liquid was inside. He transmitted this information to a central control room located away from the ISOM unit. But this level indicator was not designed to measure liquid above the 9-foot mark. During normal operation, the tower was only supposed to contain about 6.5 feet of liquid. But during startups, operators routinely deviated from routine procedures and filled the tower Startup procedures called for regulating the liquid level in the tower using the automatic level control valve. But the board operator and others had received conflicting instructions on routing the product. As a result, this vertical valve was left closed for several hours, blocking the flow of liquid from the tower. A few minutes later, operators lit burners on the furnace to begin heating up the feed, part of the scratchers, and other traumatic injuries. The wood and metal frame trailers were blown apart by the blast. Firefighters struggled to rescue the
What did you understand? I think the audio was pretty poor. Okay, but were you able to understand what happened actually?
The two instruments sensor got hit,
Hmm.
and then the spark ignition source came into it.
No, no, okay. You started off and you went to the end actually. In between. Okay, that is one part of it. Okay, okay. See, fine. I can use this board, right? Yeah. Can you, under these heads, can you tell me with whatever you have listened and understood?
Sensor you can put in
This did not work.
operators, you can put in
Which one?
operators, supervisors.
What happened to supervisor?
The person in the night shift went 1 hour early.
Okay.
No, before he didn't brief. Briefing was not given there.
Then? Supervisor is one. What about the board operator? How many?
Operator was training.
Board operator?
Was training. I think he was not properly trained.
No, no. There are two important aspects about the board operator. Sorry?
During the startup, the guy on the monitors was not qualified enough to take care of 3 units simultaneously.
Okay, okay. You also said something.
2 board operators has to present, but only one is there.
Actually, there was a manpower cut. There was a second board operator position which was removed. Actually, see, this was not a original BP facility. It was an Amoco refinery taken over by BP. So, post acquisition, what happened? They cut one operator position. Okay. What else? It also talked about how they do startup, right? How they do startup, what they were supposed to do, what they were actually doing.
They used to ignore that high level warning every time they use.
Okay. What else?
Even after the sensor showed more than 9, it started decreasing slowly.
This is again faulty, that's what he was saying actually. You're all from chemical engineering, right? What about what came out actually? It's actually not gasoline. I mean, what he was trying to say is it was a gasoline equivalent. See, it's actually raffine in the sense it's an intermediate in the refining process. Okay, you can say it's not actually a gasoline, but is it advisable to have a overpressure relief in an open system? See, what came out of, what is that drum called? So, blow down, right? Okay, so it was supposed to be a closed system. See, if you like if you have a passion for reading about such type of incidents, you go onto the net and there is a detailed 300-page report. It actually, see, one of the successful ways of how CSP presents it is it narrates the whole thing in the form of a story. If you trace back to the entire thing, in about 3 audits, internal audits of BP, this point had repeatedly come saying, if you recollect, it talks about 1950 design blow down drum. The original design was, it was an open system. Then subsequently, when it was discovered that that's not the way how to go about, so there were repeated audit points to redesign it and make it a closed system. so that even in the event of a rise, if it comes out also, it does not come out in open as the way how it had come out. Okay, fine. What else happened? Why does it talk about trailers there? Why does it talk about startup? If you recall the first 3-4 minutes, it talks about startup of the entire unit. Why does it talk about that? Shutdown for maintenance, and then this part of the unit, the ISOM unit, what it is called, it was going for a startup. What is so hazardous about startup? See, historically, if you see any steady state process, okay, with whatever amount of automation, with automation or without automation, it will be a normal one. You don't expect any trouble to happen. But what happens is, if you take in terms of trends in the oil and gas industry for the last 40-50 years world over, you will find most of the accidents would have happened, the higher percentage of accidents would have happened either during a startup or a shutdown. What happens is, actually when you do a startup, you do not go on, the entire control loop is not there, it does not provide a degree of protection. So, you gradually ramp up the volumes, you gradually raise the temperatures, you gradually raise the pressures. So, during that point of time, you do not have full control on the system, that is how it is designed actually, and you cannot, because it actually sort of transient environment in which you operate. Same is the cases when you do a shutdown. Okay. So, it says like when you, that is where there is a concept called pre-startup safety review. Before you start a unit or a process, you do a thorough checking to ensure that these type of things do not happen. Okay. Now, what about the explosion? See, this is okay, I mean this is what happened, it is fine, okay, maybe there are some 3-4 aspects which you guys have not told, but that is okay. What happened subsequently?
Truck drivers forgot to switch off. The truck drivers forgot to switch off the ignition.
Forgotten, he was not able to, because what happened, the engine was already on, and you know this the vapor was so this thing that it went and it started, he was not able to switch it off. Okay, what happened subsequently?
They ran away, but what was the reason? Like I was not able.
No, after that it's exploded, right?
Yeah, it's exploded.
Okay, did you see the intensity of the damage? Okay. So, that is like that is where it talks about, see there are very specific reasons. Did you think why the trailers are kept so close to the process unit? That is actually not the intended thing. See, what happened is those trailers were there largely as a temporary setup because the refinery was undergoing shutdown. So, like where you have lot of contractors coming in for doing their work, and there are some administrative controls to be done. So, that is where the temporary trailers are put up there, but actually what happened is the people who got killed are the people who were there in that trailer. Okay, so, this is something where an important aspect. Hold.
Trailer is
Okay, trailer is a temporary. Okay, what did you say? Okay, you seen 40 feet ISO containers? You see ISO containers, right? The big boxes, 20 feet, 40 feet ISO containers. What happens is, it's actually a mobile office. You can take it. It's like it has sandwiched panels, and like it has power sockets. The moment you place it somewhere, you plug in, you will be able to use it as an office. This is what largely is used in projects. You go to any project site, you can't go and build every time. So, you simply drive it, park it there, plug in from an EB power source, and then you can use it. Okay.
It's a closed system, is it?
It's like an office space. It's like this room. It's like this room. That's it. Except that maybe here it's made of your brick and RCC. There it will be made of wood and some sandwich panels. Maybe it depends. Like if it is like you may have a steel reinforcement, or it may only be a wooden reinforcement. Okay. Now, what do you mean by sighting? Have you placed what? Not only equipment, we talk about the overall process blocks. Okay, you have an industry, okay, you have a layout, you have storages here, you have control room here, you have process blocks here. Now, which should come where is what talks about sighting. In fact, there is an API standard on sighting. Post this incident, the standard itself was reviewed. Okay. Now, what I was trying to tell you guys here is that you see here variety of hazards, the consequence of it, what happens. So, there is no one single technique which will help you to identify all these hazards. Okay. So, there are multiple techniques which are available and depends upon at what stage in the life cycle of a particular facility you want to do. Okay. So, that is what is that, which is something which I want you guys to understand. Now, what we will do as we move forward and talk about various techniques, I will try and give examples from here, so that you will be able to correlate in terms of why it is important. Okay. Now, what is process hazard analysis? It's a systematic approach for identifying, evaluating and controlling hazards of processes. See, it is not only about generally talking about process, it is about process involving highly hazardous chemicals. That is the key. Okay. Because you go to cement industry, they will also call it as a process, but the degree of hazard will be lower. Okay. So, it talks about process involving highly hazardous chemicals. Okay. Why is it needed? I think it is a fairly straightforward thing. You cannot control something which you do not know what it is, right. It is as simple as that. What you talk about in your management jargon, what you cannot measure, you cannot control. It is as simple as that. So, risks cannot be controlled unless we know about what is that, and also determines what is the potential causes. So, as we go through each of the thing, you will also know what is the cause, what is the consequence, right. And also it talks about this is actually a library of information. A PHA which is done for a particular facility gives you a bible of information in terms of what are the inherent hazards in the process. The most important aspect being, you are expected to train your employees in telling them, boss, look, this is what you are trying to do. If you do not follow these processes, this is what is going to happen. Otherwise, it will all be Greek and Latin from, he will not understand what you are trying to say. So, you again trace it back to Bhopal. What happened? One of the reasons which is cited to increase, like which increased the severity in terms of number of people getting affected, was because Union Carbide at that point of time was not willing to disclose the chemical properties of MIC, meaning unless you know what treatment to give. See, if you have inhaled some chemical, unless I know what chemical you have inhaled, you cannot give a right type of treatment, right. Similarly, I think in industrial hygiene, I am not sure whether it was touched upon, it is a topic under occupational health, there is something called antidote. If somebody inhales some chemical or somebody ingests some chemical, and this chemical is to be given so that it neutralizes the effect of this particular hazardous chemical. So, same way your PHA provides you a bulk of information in terms of what hazards the facility poses and what controls you have already taken, and that is something which the industry is expected to use to formulate its strategies in terms of mitigating its risk. And also variety of ways, like we will see that in terms of how it is, like it is used for the purpose of facility siting, it is used for the purpose of human factors. Why, can you explain why this is important? Why there are 2 operators required, why not 1? How many of you have visited an industry, a process industry? Very good. Which industry you went? Paper industry. I am afraid I cannot give you an example from that, because that is not controlled from the control room. Any process industry? No.
Fertilizer.
Okay. Fertilizer you have gone. Okay. Have you gone to the control room?
Yeah.
Okay. So, from that context, can you say why this is important? Why you require 2 operators, why not 1?
There are like quite a number of panels, so it was not like humanly possible for one guy to look into all the.
Okay.
And also discussion wise also, like you can talk.
Anything you've seen any control room in paper mills? Okay. Okay. How many people were there? It was controlling what? The core process or the power plant?
I saw in the power plant.
Power plant you saw. Very good. Okay. How many operators were there?
3 operators are there for one process controlling. Means one is looking for the water part, means how the steam is generated,
Correct.
and
That's how it's
another one
managed.
is looking for the fuel part.
Okay. Fine. See, one of the reasons here is that, as you said, like as you were saying, she was trying to explain, like somebody looks after balance of plant, somebody looks after raw material feed, somebody looks after the core process. The reason being that you see the historically the human body in a particular 8-hour shift can only respond within that specified time for so many alarms. Like for example, I am in an 8-hour shift, my body is designed to immediately respond if I get an alarm 1 in 8 minutes. If I get more alarms than that, then the response time or the way how I logically analyze the response to a particular alarm will get affected. Okay. So, assuming like one guy looking after 3 panels and one going for startup, the one going for startup is something which has to be monitored continuously, right. So, if one guy is one guy is designated to manage multiple people, then you will have a problem. Okay. That is where you see a last line, human factors. So, human factors in process safety is more from this perspective, is in terms of how does an operator at field level also responds to a particular emergency in terms of how he has understood and handling it. Okay. This any time in the last 5 weeks you heard about it? No. Okay, fine. See, you find out, like you do all the hazards, you identify, and then you understand that there is a risk or there is a hazard there. How will you eliminate it, or how will you want to address it? Okay. This is the hierarchy of control. The first control is to eliminate it. Like for example, there is a hazardous chemical which is being used in that particular process. The first simple methodology is find out whether that can be eliminated at first place itself. Can you live without that? That is the first question. It is like your argument today on nuclear power. Does India need nuclear power? Can you afford to live without it? Just giving an example. Okay. Second thing is substitution. Okay. I want the process, I cannot live without the process, but can I have a chemical or a substance which is relatively lower in the nature of its hazardous properties. Okay. That is substitution. Now, I am not able to achieve both of it. I require that chemical, I require that process to be done. Then what are the engineering controls that I have? What is an engineering control? Can you give an example based on what we have seen?
Safety valves.
Very good, excellent. It is an engineering control. Okay. So, safety valve is an engineering control, or you have a system wherein it detects something and shuts down a particular pipeline or a leak, a gas detector, even inherently designing your vessels itself. Okay. For example, you have a process reactor, then what is the thickness, what is the pressure for its design, what is the cycles of operation for its design. These are all things which falls under engineering controls. What is administrative control? It is like saying, like train the person, make him aware of what is the hazard, follow a work permit system, all that forms administrative controls, and last resort is PPE. Okay. So, this whatever you do in your life with respect to safety tomorrow, this will remain the fundamental. Anything that you work on safety engineering is based on this. Not only safety engineering related to process, it also relates to your occupational safety. You talk about machine guarding, you talk about exposure to noise, talk about exposure to dust, whatever, everything follows this same thing. Now, why I want to touch upon this point is, when you do a hazard analysis and when you talk about arriving at a risk control, this is the hierarchy which generally anybody follows when you are trying to come out with a control. Okay. Now, for a time being I will park this case study. Okay. Now, this is broadly in terms of when you talk about hazard identification, process hazards, hardware hazards, control hazards and human hazards. Okay. There is an Indian standard on hazard identification, it is called 15656. Okay. In case if you have an opportunity to access in your library, have a look at it. It broadly gives you an understanding of how the hazard identification process is done. Very good, excellent. Anybody had an opportunity to go through? So, it is a pre-read, is it? Okay, fine. So, these are the various techniques which we are talking about. Okay. It's hazard. Why both are different, I will explain to you as we move forward. There are some techniques which focus in terms of helping you to identify the hazards. There are some techniques which will help you to also quantify hazards. See, end of the day, that is the most important aspect. Okay. Now, what are the techniques which help you to hazard identification is that we will go one by one. Okay. Now, I will not go in depth in this, I will just briefly tell you what is important. Can you help me to trace the life cycle of an organization or a project? You are an entrepreneur, okay. So, tomorrow you want to start up your own facility. So, what will you do first? What is the project life cycle? I am asking very fundamental questions here. What is the project life? Maybe I think you didn't get my point. What I am saying is, okay, you want to set up a plant or a factory. What are the steps you follow?
You would go investigate about the site.
Okay, fine, okay. No, you tell me from a conceptual thing, don't straight away jump into the ground.
Feasibility study.
Very good, excellent. Okay. Okay, what next? Your feasibility is done, you have decided that you are going to go ahead. So, what is the next step that you do?
Engineering design system.
Very good, excellent. Okay. Are there some types in this? Okay. My handwriting is pretty poor, you will have to live with it. Okay. What is the next step?
What is that? Feed in?
I will explain to you. Okay. So, you have done engineering, what next?
So the engineering.
Layout of the plant.
Engineering. So safety also includes the engineering part?
Yes, that is why we are here. That is what is PHA all about. How do you integrate safety? That is what I am trying to tell you now. Okay. What is the next step? I have engineered. So, what next?
Precautions in case of any.
No. Look at it again at this level. Do not get into the finer aspects of it. I have done engineering. What next? See, you are building a house here. A plan is approved. What else you will do?
Construction.
Start construction, right? Then
Production.
okay, commissioning. Commissioning and then your production or your steady state operation, whatever. Okay. See, these 6 stages. Okay. 1, 2, 3, 4, 5. Okay. In between there is something called pre-commissioning and then you come to your production. Fine. Largely you take it as these 5 stages. Now, how do you integrate safety across all these stages is what your PHA techniques are trying to do. Okay, this is at one level. Okay. Now, what technique you use at various levels, it is entirely different. Okay, and that comes with degrees of experience, expertise over a period of time. It also depends upon the client. Now, somebody asked me what is feed, right? I think you are asking me what is feed is nothing but front end engineering. See, it is detailed engineering is where you get into the finer aspects of it. Like for example, you want to lay a pipeline, you will say like it's 12-inch, carbon steel supported at so many points, above ground, underground type of thing. Feed is slightly one level above. You only know that you want a pipeline for 10 kilometers from this place to this place. You do not even know what is the diameter, you will not even know how much of the pipeline is going to be above ground, below ground, whatever. So, that is at this level. So, what happens is all these hazard identification techniques, it is applied at various stages in terms of the project, so that you do not have a surprise tomorrow when you operate a plant. Please understand. See, there is a lot of limitation moment you start operating. You start operating a plant and like as an external expert I come and say like no, these are the risks you have not addressed, you include all this. You can't shut down the whole plant and change the whole design. That is not going to happen. Okay. So, this is where integration of safety at various stages comes into picture. Okay. Now, you have this overview. Now, I will try to link it to each of what we are going to say. Okay. Now, I am getting into the techniques which I use for hazard identification. Okay. So, in the subsequent classes you will have a detailed analysis of each of those techniques, how it is going to be applied and all. I will give you a broad overview of what is that technique and where it is used. See, one of the most simplest techniques is checklist analysis. Okay. So, you want to do maybe a desktop review or you want to do a rapid review. For example, you have a boiler. Now, you want to sort of either at the design stage or after it is commissioned before startup you want to do an analysis. So, what you do is that you have a standard set of checklist, you know what are the points to be observed and then you use it to see whether the risks have been, whether the appropriate hazards have been identified, what is the risk and whether it is acceptable to you for you to continue to move forward. So, this is one of the most simplest techniques which is used, but it has its own limitations, because it can be used on a very discrete type of equipment and like where the equipment will not pose any additional hazards. It is proven and it is used in that way only. For example, you take boiler standalone, like a boiler of so much so capacity of this make, these are the standard set of hazards, unless you try to tamper with the way how it is being operated. Per se it will have a standard set of hazards and could be used in a case where you use the checklist to just go through each of the points, assure yourself whether those things have been addressed or not. Okay. Safety audit is another technique, but as the terminology goes, it is actually an audit process. What is an audit? What is your understanding of audit? That is financial audit. Okay. Yeah, you say checking the balance sheet, okay, against what? Against standards. Standards, what else can it be? Against standards, against? See, whenever you talk about these things, for you the first thing should be law of the land. Please understand, it is going to be the law of the land. That is the fundamental based on which you will operate. For example, you are in India, you are expected to comply with certain requirements, right? Then only comes the standards. Not all standards will have the judicial standing. See, tomorrow you build a plant, assuming that there is an incident and it is gone to the court. You can't go into the court and say that no, I will not follow Indian law, I have designed as per this standard. They will say no. If you have decided to operate in India, you need to follow this thing. So, audit is nothing but where you do a systematic examination to verify whether the existing methods, practices, whatever is as per statutes, standards, and if the client is so magnanimous, he wants you to look at all other applicable good engineering practices, whether he is following it also or not, you will take that. But if you ask me, a safety audit is not one of the best techniques for a process hazard analysis. The reason being, it is an audit, and any audit for that matter is a sample audit, correct. Like you go to a particular plant, you have a time limitation, you are there for 2 days or 3 days, you look at what a particular operation is done, on that particular day how is the operator behaving, and based on which you are trying to frame your observations and recommendations. So, that is not going to be a foolproof method, okay. But this technique helps you in terms of broadly understanding whether this particular plant has identified hazards arising out of exothermic reaction, has it identified hazards arising out of electrical source of ignition, has it identified hazards related to occupational safety. So, it will throw you large buckets of areas where you need to focus further upon. Then for each of them what technique you can use, you can decide upon. Like for example, so a typical safety audit if you look at goes through variety of things. In fact, there is even an Indian standard on safety audit, it is called IS 14489. So, this is how the report looks like. What is the applicable standard? What is that you have seen in the site, whether it confirms or not, what is the observation, what is the recommendation, what is the priority. Okay. Okay. This is another interesting technique. It is called what if analysis. Okay. And this you can use it in process, you can use it in manufacturing, or you can use it in any other process where you want to use it. The beauty of this technique is that it helps you to brainstorm. Again, it is a team exercise, it is not like one guy sitting and writing the whole thing. So, the what if questions will lead you to analyze more. It is not opening, PDF is not installed. PDF is not installed. Okay, I'll okay. See, what it does is you take a particular section of the plant. For example, let us assuming like since you guys have gone to the power plant, assuming that it is a coal conveying system. Okay, you have seen coal or you have seen bagasse? Coal. Okay. So, assuming it is a coal conveying system, right. So, the question is what if there is fire in this coal conveyor? Okay, that is the scenario which you talk about it. What could be the various causes? What could be the causes? No, what could be the cause for fire? My scenario is fire in coal conveyor. What could be the various causes? Excellent, static electricity. Okay. External fire. Okay. Heat generation because of the bearing, whatever, fine, okay. Yeah, fire, okay, group it under that, fine. So, what is the consequence? What will happen?
Fuel ignites, coal might ignite.
That is the immediate consequence. What will happen after that? Shut off, it will, okay. So, what will happen? Fire in conveyor leading to shutdown, right? Plant cannot operate, right? What is the safeguard? Very exactly. See, now this is the key. Okay. Now, what safeguard you are talking about here? What safeguard you are talking about here should mitigate your cause, not the consequence. You understand what I am saying? Grounding. That's what. That's okay. I am talking about first point. Just as an example. No. See, what happens generally? What people try to make mistake is you try to mitigate the consequence. No. This safeguard is permitted as a safeguard only when it mitigates your cause. Otherwise, what will happen? You will give credit to something which it is not actually technically permitted. So, this is what you do. So, you look at the safeguard, if it is not sufficient, you will convert it into a recommendation. So, this is what happens in a what if analysis. Okay. Okay, FMEA, its failure modes and effect analysis. See, this is largely used in what I would say equipment, or it is even used in your sensitive electronic, maybe your what I would say your printed circuit boards, or it could be a piece of electronic device, whatever it is. What happens there also is that you first define the failure mode, look at what is the severity, what is the probability of it, detection number and risk priority number. I will quickly give you an example. Okay, the PDF will not work. Okay. Now, what happens here is that you look at what is the failure mode in terms of that particular failure has happened. What is the cause because of that failure? Operational mode, it is in operating in which particular state of the operation. What is the effect? See, for example, now you have a valve which is operating beyond its limits. What happens? Like assuming there is a control valve, it is operating beyond its limits. It is supposed to open only for, let us say, a quarter turn, it is operating for half a turn. What will happen? Assuming that it is a valve which is fitted in the nitrogen line. So, it will let more nitrogen flow through the line. Now, that can result in pressurizing a downstream equipment, or you may result in loss of nitrogen in case if it is an open system type of thing. That is what is the failure effect. And what is the failure detection mode? How do you detect that failure? Assuming downstream it feeds on to a particular vessel and pressure increase is there in that vessel, and that is detected to a pressure transmitter. So, if you already have that, then that becomes a detection mode. Okay. And then in terms of compensating provisions, okay, in the event of increase in pressure, what is the existing control the system has to readjust itself to ensure that the intent is maintained? And severity class, in terms like assuming that the failure happens, is it going to, like what happened, is it going to injure somebody, is it going to kill somebody, is it going to result in a fire? So, all that is what happens in a failure modes and effective analysis. Now, here there are multiple techniques available. In fact, there is an EN standard also. So, it depends upon for which type of equipment you want to use this technique. Accordingly, you can customize your probability table, you can customize your severity table, you can arrive, you can whole point of this can be customized. Generally, my experience I have seen is that you go to steel industry, your typical furnaces, because what happens, furnaces are fairly complicated because the parameters are so complex to monitor, be it gases, be it temperature. So, generally people will prefer doing an FMEA over a routine HAZOP, it will not work out. So, sort of electromechanical interface is what generally people use. For example, how do you ensure that your utilities, even in this building, let us say, for example, you have air conditioners, you have chillers, you have electrical panels. If you want to analyze from a risk perspective, which is having a high degree of risk, FMEA could be a classic technique. HAZOP, you have heard about HAZOP? Okay. So, see, this is my opinion, see, this is one of the most used and abused techniques in industry. Like, it's become so extent, people try to use it in wherever it is not applicable also, people generally in industry try to use it. But one unique thing about HAZOP is that it only talks about hazard. What is OP in that? What is that? What is operability? Can you give me 2 examples of operability? What is operability?
Conditions of operation for process like temperature, pressure.
Conditions of operation is right, but what you said later is not right. Take that clue from that, conditions of operation. Have you guys seen a HAZOP report any time? No. Okay, fine. See, I will just give a simple example. Maybe subsequently in the next few classes you will try to understand it in a detailed way. See, for example, a valve is there which is at 3 meters elevation. A valve, control valve is there which is at 3 meters elevation, and you expect an operator, assuming that he sees a parameter, he wants to go and operate that valve. Will he be able to access it safely? Okay, that is the operability part of it. Same you can apply this to anything, like be it a location where there is no proper illumination, you need to see a reading, or be it in a location where you need to install a critical equipment, but then it will not have its access from a maintenance perspective. Okay. Not really in terms of ergonomics. See, ergonomics is purely a man-machine interface. Okay. You have very little influence of the working environment on him. Okay. Whereas here in terms of operability, okay, the example I gave you is a man-machine interface, but it could be even with respect to the equipment itself. There are some sort of equipment where you cannot exercise control beyond its intended design. It will have certain set of things, and then you cannot have monitoring on it. Whatever you will be doing is reactive. Something has happened, it will show up, then only you will be able to do type of thing. You will have a better understanding maybe with examples as you see in the other.
Do maintenance, they want to go and approach a pump or something. They will not go there. Accessibility will not be there to operate the pump or to control the pump. Maybe if it's a DMP pump, they will not be able to go into it.
See, I will give you an example. You go to process industries, you will find it very familiar. Like you have a big pump. It's a transfer pump installed. All along it, you will have equipment. Now, what happens is during project stage, he would have happily installed this, because surrounding you had path to move, you had equipment to bring in and install. Tomorrow, if there is some repair, I want to remove this up. How will you do? That is an example of operability. Operability, maintainability, whatever. Okay, what are the advantages? It's open ended. It identifies all the process arts. It's a very structured technique. Like for example, now today we are doing a HAZOP for a new gathering station for one of our clients. The HAZOP today is what, 22nd day in the back, it's something like we are doing HAZOPs of 280 P&IDs. So it's a very rigorous exercise, and it's a team exercise. The HAZOP chairman leads the exercise. You have a set of guide words and you go through that, discuss it. And that is where operating people share a lot of their experiences in terms of like what changes they require, what has happened if this is the same design philosophy, why you need to change it, do you require a control system here, do you require an additional valve here. So, all of those come into picture. Disadvantage is it can be time consuming, relies on having right type of people, that is the most important aspect. Does not look in terms of low probability high consequence. Okay, I mean this point is sort of what I would say 50-50, because today you have HAZOP techniques where you can do risk ranking in HAZOPs also. Because what happens at the end of the HAZOP, you have some 500 recommendations, but the client has to implement. No, each of recommendation costs money and also time. It's not only about money, it's about time. For example, you have a 24-inch pipeline. HAZOP study says that you add one more valve. To manufacture a 24-inch valve takes 8 months. Imagine that your project duration is 2 years and you have one component which is having plus 8 months, whole project will get derailed. So that's also one of the points in terms of if you don't have a right type of people, if you are not able to identify right set of risk control measures, where you will have a problem. And this is what happens, like where you have set of guide words, deviations. Now guide words are like in terms of pressure, with parameters like pressure. So what happens when you have high pressure, what happens when you have low pressure, flow, more flow, less flow. So each of that is combined, and then you have what is the cause, consequence, and you have the risk ranking which I told you there, what is the effective safeguard and what is the recommendation. Okay. Okay. When it comes to hazard analysis, this is one terminology which you will frequently encounter. It is called HIRA, Hazard Identification and Risk Assessment. Okay. The reason why I want you to understand this is, you can see here 2 standards mentioned about it. Okay. Now, this is not very widely used in process safety. I want you to first have an understanding of it. This technique HIRA is largely used where it is task oriented. Like for example, in manufacturing, you have a grinding machine. Okay. As an operator, my task is to reduce the diameter of this wheel. So, I pick up that wheel, I fix in the grinding machine, I use the right type of tool, and then I reduce the diameter of this. Now, is this related to process safety or occupational safety? Hazards coming out of this operation. I think got lost. I will repeat what I said. See, I am giving an example where it is a grinding operation. You have a grinding machine. Okay. I have a grinding wheel in my hand. The intent is to reduce the diameter of this grinding wheel. Let us say maybe diameter from 300 mm to 295. Okay. So, I take this grinding wheel, I fit it in the grinding machine and then I use a grinding tool. Okay. So, the machine, the wheel runs, I use a stationary tool, I use it to reduce the diameter of this grinding wheel. Now, any incident which happens here, is it going to be an occupational safety related incident or is it going to be a process safety incident? How many of you process safety? And I have failed, I am getting 0 marks now. Okay. Now, that is the reason why I gave this example. I want you to note that shift. Till date we have been talking about process safety. Okay. Now, we have come to this HERA. Okay. Now, why you say it is process safety? Sorry, what is your name? Avinash. Why Avinash you feel it is process safety?
Because you are using a grinder, you are changing out the dia, because of the changing of the dia, there is some.
But what is process involved? I said, like, I asked you to note in process safety 2 words apart from the word process. I said, don't get carried away process. Process involving what? Highly hazardous chemicals. Yes. Grinding, is there any chemical involved? No, right?
No, highly hazardous chemical.
Chemical.
High severity, you said.
No, that is the second point. See, what is the first point? We said any incident, it involves a process which handles highly hazardous chemicals which could result in fire, explosion or toxic release. Okay, this is process safety.
Okay, in short, we can say it's high frequency.
No, you cannot shorten it to that. See, inference is not that, understand. High severity, low frequency is one of the characteristics of a process safety incident. That alone does not quantify you or does not qualify you to call an incident a process safety incident. Okay?
But just the main understanding between severity and
No, for a moment you park your severity and frequency. Don't get there.
This example was actually what? Fine. Is it occupational or
It is occupational safety only.
even from severity point it's correct, only one guy is there.
Yeah, correct, exactly.
It's not severe.
Exactly, that is what I was about to tell him. See what happens here, see there is no chemical involved, right. Okay, even if you are going to use a cooling agent there, a cooling agent is a non-flammable material, even in the wildest of dreams if you have seen a grinding process. So, it is an incident involving a non-hazardous chemical, okay, A. B, as Dipin was saying, it is an incident involving a person, even if he has got killed, it is one person. Okay. So, it is an occupational safety incident. Now, this technique is used more to identify your occupational safety and health risks. That is what I want you to get. That is why I gave this example. Okay. It is not a very successful technique for identifying your process hazards. Okay. Fine. Okay. I think this is what we did. This and all I will skip. Okay. By any chance you guys have heard about this fault tree analysis? I think it does come in your engineering. I think maybe a very cursory look of what it is. Okay. Now, coming to the analysis part of it, this is one of the what I would say a basic technique which is used where an incident has already happened. You want to try and reconstruct in terms of understanding why this whole thing has happened. That is why it is called, you look at the name, it is fault tree analysis. Fault has already happened. So, these are what are the various symbols that I think all of you would be very familiar with, this AND gates and OR gates and what it is. So, this is how it is done. See, very simple example, you can look at it, like, and it is a dark room. Now, when can a room like why can it be dark? It could be either power off or both the lights are burned out. Now, each of it you go and start dissecting it into the root cause. This is how a fault tree is created. Okay. Another one is event tree, where you are now identifying hazards and consequences from, you can see here, Look at the difference. It goes in the different direction from where you talk about. There you talk, like for example, in fault tree, if there is a fire which has occurred, you start from the fire. Okay. You have release, you have source of ignition, why the release has happened, what are the various causes, ignition, from where you have got ignition set of sources, you look at it. But here you start from the event, not the final event initiating. For example, gas release. What happens once there is a gas release? You can have both in terms of, if gets immediately ignited, what will happen? If there is a delayed ignition, what will happen? In case of a delayed ignition, you can have a possibility of an explosion. Immediate thing, like for example, if it is a jet fire, what will happen? And here what you try to do in event tree is that at various stages you also try to look at in terms of what layers are there which will stop propagation. For example, if it is a gas release, you have a gas detector, it is immediately going to instantly detect, it is going to shut down the process, so that your loss of containment does not get aggravated, you do not get more gas coming out of it, right. Okay. I do not know if this will be to this thing. Okay. There is something called for many of you who are interested in hardcore, what I would say, instrumentation cum reliability engineering. This is another upcoming field, it is called functional safety. Okay, it is called functional safety. Now what it does is that, I think in this incident we talked about faulty sensors, right. Okay. Now how do you ensure that the sensor does not malfunction? The basic design of the instrument itself, how do you ensure that it is of high degree of reliability? Okay, that is what functional safety is all about, and the key thing here is that does not look at the instrument per se, it looks at the entire control system. The instrument could be the point of detection, it could be a pressure transmitter, the signal goes to a control system and then maybe it actuates something, it could be using a valve, you shut down a pipeline. So all these three components, how do you ensure that at any point of time when it is required to operate, how does it operate? The availability of the system in terms of at a very high thing we are talking about, it is called SIL 1, 2, 3, 4 not much, 4 is largely followed in aviation and nuclear industry. Process indices you have SIL 1 and SIL 2. So that is what it goes into in depth in terms of identifying various loops, how do you classify, there is a separate study by itself. Okay. QRA is nothing but I think what you saw in terms of in that video clipping, like what it did, it tried to recapture what quantum of material could have got released, how did it get its source of ignition, moment this happens, what is the consequence, be it heat radiation, be it explosion, or it could be even toxic release. For example, chlorine tonner, like which you use it in your water treatment plants and power plants and all, you have 1 ton chlorine, moment assuming that the whole tonner ruptures and the entire chlorine comes out, till what distance it will spread and how it will impact people, that is what QRA is all about. I think you are going to have maybe in week 10, 12 detailed sessions on QRA. It's a very interesting subject, and you have lots of, what I would say, the outcome of QRA study is very important for the industry. Right from that, how do you select the type of control room, how do you locate the control room, how do you locate your critical structures within the plant, and today the government gives approval for a new facility based on the risk analysis report. If the risk analysis report says the risk is unacceptable, the industry is not permitted to be set up unless certain controls are in place. Okay. So this is what I have largely in terms of what is PHA all about. Maybe we will, can I take another 10 minutes? Dipin? what you saw was an effect of explosion. What you actually, when you do analysis, there will be a table which will show at this pressure, at this bar of pressure, the effect will be shattering of windows. That is what we quantify. This is exactly what it means.
Accidents that the CSB has investigated caused by runaway chemical reactions. Accidents resulting from reactive hazards occur too frequently and often have serious consequences. Behind me on this concrete pad, there used to stand a structure some 50 feet high that had a reactor vessel in it, in which the company that operated here, T2 Laboratories Incorporated, manufactured a chemical known as methylcyclopentadienyl manganese tricarbonyl, or MCMT for short. The entire structure and reactor vessel were blown away in the explosion.
T2 produced MCMT, a gasoline additive, in batches using a 2,500-gallon reactor. An operator controlled the process with a computerized system in a nearby control room. In the first step, liquid chemicals and sodium metal were loaded into the reactor, heated, and then mixed with an agitator. The reaction produced hydrogen, which was fed into the atmosphere. In normal operations, when the temperature reached 300 degrees Fahrenheit, the operator would turn off the heating system. But because this reaction was exothermic, or heat-producing, the temperature inside the reactor would continue to rise. At 360 degrees, operators would begin to periodically fill the reactor's cooling jacket with water. As the water boiled, heat was removed, controlling the temperature. However, on the day of the accident, the CSB found that the operator tried to cool the reactor as usual, but the cooling system likely malfunctioned, perhaps due to a blockage in the water supply piping or a valve failure. The temperature and pressure inside the reactor began to rise uncontrollably in a runaway chemical reaction. T2's co-owners returned to the plant after a worker called to report the cooling problem. While one owner searched for the plant mechanic, the other went to the control room. Concerned about a possible fire, he warned employees to move away from the reactor. Inside the reactor, the pressure was still increasing, reaching 400 pounds per square inch and boosting the rupture disk. Witnesses heard a sound like a jet engine as high-pressure gas began to vent from the reactor. But it was too late. Within 10 seconds, there was a massive explosion, equivalent to about 1,400 pounds of TNT. The blast damaged buildings over 1,500 feet away. Debris rocketed up to a mile. The co-owner and the operator in the control room were killed. 2 operators further away died from flying debris. 32 other people were injured, including 28 at nearby businesses.
This facility immediately was a shock or a surprise, and all of us were shaken afterward.
What happened? What happened in this incident? Which technique would you feel would have been able to identify, would have successfully identified this hazard?
QRA, but that
Hmm. Hmm. Very good. After the release is QRA, correct? Okay.
Failure mode analysis
Okay.
or fault tree analysis.
Fault tree, see, fault tree is generally used as an investigation technique. Is mostly used when you do your incident investigations.
But they can do in the starting also. So if this
What is this? Okay. I've written something. I've given the clue already.
no flow of cooling. Event tree analysis.
What is the technique which uses a set of guide words, links with parameters, discusses about deviations and causes? Okay, that's why I gave this hint of writing no flow. Okay, so I just wanted to give an example of, see, that's what I am saying. You might have a number of techniques, but what is very important is at what phase you use. For example, HAZOP. HAZOP is one technique which you can use it at any phase you are there in a project. You can use it at feed stage, you can use it at detail engineering stage, you can use it during commissioning. There is something called commissioning HAZOPs. You can use it in steady state operation also. For example, if you take in India for oil and gas industries, every 5 years, whether you change the process or not, you are expected to do HAZOP of your entire process plants with respect to oil and gas. It is a mandate. So, in this case, HAZOP, if it had been done with the right intent, and as I was telling you, it is not only doing HAZOP and getting set of recommendations about implementing it, otherwise the risk remains unmitigated. And QRA, as you said, like by that now you have understood in terms of the consequence what happens is, then accordingly is based on what you design your control measures. Okay, fine. So, that is what I had with respect to an overview of what is PHA, what are the various techniques. So, subsequent classes Karthik will explain in terms of maybe around 5-6 techniques is what he is working on, which we will go in depth into each of them. So, you will be able to understand the difference in terms of like how the terminologies are used, why it is effective, why in certain cases FME may not be effective, certain HAZOP may not be effective. So, all those you will have a better understanding. Any questions you have? Any doubts?
Part that was not clear to
Sorry?
me. HAZOP, it was not clear to me.
You want me to undo? Okay. Okay. See, what happens here is, assuming that you have a pipeline. You have a valve in this pipeline. Okay. What happens in HAZOP is that you will have a set of like a pump, a pipeline, and which goes and stores in the storage tank. First, what you do is you choose something called a node. A node is a set of demarcation which you do on the P and IDs. You know what is P and IDs? Okay, right. In which you choose your boundary for which you want to discuss. Okay. Now, it could be only a section of this pipeline, or it could be a pump, or it could be a combination of both, or it could be the tank alone. Okay. Now, assuming that you have chosen this tank as your node. Okay. Now, you take flow. You want to discuss about flow. Okay. And you want to use the deviation no. When can no flow happen? When can no flow to the tank happen? So you start writing there cause. What will happen if flow doesn't happen to the tank? What can happen? Why you say that? Why you say that? See, it depends. Huh? See, assuming the same tank has an agitator, or you are mixing two substances, which is what typically happens in your reaction vessels in pharma industry and all. So, if you don't mix it in the right composition, you are having A lower than B, then it can result in some other type of thing. What will happen if there is more flow? When more flow can happen? Valve is malfunctional, meaning see what happens here, like moment you start doing it, you will understand it is purely dependent on the design intent. If my design intent itself is to keep the valve half open, then accordingly you will discuss. Same thing applies to pressure. Okay. Now what happens? Okay. So which is what you try to do with a set of parameters, and that is what is the deviation all about. Okay. And it is one of a very structured techniques. There are standards available. There is there is a British standard on HAZOP. Okay. It's fairly straight process. Only thing is you need to have a very thorough understanding of the process, and the team which is there, as I say again, it's again a facilitator led study. So as a chairman, I will only lead the team, but the team has to come up with like what will happen, how more flow, less flow can happen. Now where the input comes is, like for example, you talked about the valve. Can this valve malfunction? You have a valve passing. Now if you have a valve passing history already, then you have like then you look at in terms of this valve seat. Do you want to go in for a specific material which is compatible with what chemical you are using, or if this valve comes in an area where there is a possibility of jet fire and this valve can get damaged, but from an emergency perspective you want this valve to be protected, so that even in the event of a fire you want to close it from control room, then what is the fire rating of the valve? So all those things will come up once you start discussing, take from the P&ID, mark the note, go to each of the parameters, use the guide words, arrive at what is the deviation, cause, consequence, what is the control measure. Okay. Fine. Any other thing? I think I already got an indication saying time over from there. So, okay. Fine. Thank you, friends. Okay.